Everyone to our International Inverse Problem Seminar. So today we're happy to have Alexei Novikov from Penn State, which will be talking about imaging with incomplete and also corrupted data. Thanks a lot for joining us, Alexei.
Thank you, Knut, and for inviting me, and organizers for giving me the opportunity to speak here. I will be talking about some aspect of our project, which hopefully will be very simple, sort of the algorithmic aspects of recovering the images. I will start, and then again, as usual, please interrupt me as much as you like, because that makes it more lively, and also I will at least feel whether you follow what I'm saying. Maybe I should slow down or speed up, but please do stop me whenever you have questions. So I would like to cast our problem in a very simple for linear algebra formulations, because in the end of the day, when we solve an inverse problem, what you have is a system like that. This is the data that you measure. There is an imaging matrix, and then there are unknowns. Rho stands here for reflectivities, so scatterers, and then there is a noise. So you're interested in finding rho given the measurement, one measurement or many measurements B that you obtain in your imaging experiments. And as I said here, you use some sort of some known imaging matrix A, and the typical setup is that the number of measurements is much smaller than the number of unknowns, and in our case that we were interested in the signal, this rho, the one that we are trying to find, is sparse, and the sparsity of the signal is also much smaller than the number of unknowns. So and then of course, in any imaging problem, the objective is to find a signal. More specifically for us, the more important part was to find its support, because we were mostly interested in questions of detection of targets, and the interest is to look at imaging when the number of unknowns grows and becomes very large. So this is the motivation, and as I said, the main motivation for us was inverse problems in wave propagation. So the setup there is, for example, radar imaging. You have a radar that where you have transducers, you have sources that emit, for example, electromagnetic waves, and then you have a target, an imaging window, where you have scatterers. So this is a reflection problem. So you emit waves that scatter from the scatterers, and then they go back, and you receive the signal back on the array. So that's the motivation for the problem. However, if you look at the formulation that I had on the previous slide, on this one, this is just a linear algebra problem, and as such, it is well studied, and there are methods that address the sparse recovery problems that are called L1 minimization methods that were extensively studied recently in signal processing, machine learning, and things like that. So we were interested in seeing how much mileage you can gain in imaging of points, or radar imaging, for example, of point sources. So, and looking at this picture, one could see where this natural assumptions that I mentioned on the previous slides come from. So, for example, the number of scatterers so n is the number of pixels in your image window, the way you look at you discretize your image window, and of course you see that the number of scatterers, so the support of the image, is naturally smaller than the number of pixels you use to discretize your image window. It also the number of measurements. So where the number of measurements come in. So the number of measurements n is the number of points on the array. It's the things that are sitting over here, and naturally it's also smaller than the number of points in the image window. So and as a main remark from the point of linear algebra, this transformation, when we want to find rho, if we have measurements, even in the absence of noise, is not invertible, and one uses L1 regularization methods as an approach to find the solution. So I'm going to show many pictures, hopefully, and they will be of two flavors. One of them, I will be showing you images and how well we can restore an image. So here's an example of that picture. Even though most of the imaging was done in 3 dimensions, I will show you 2-dimensional. You can think of them as slices, for simplicity of representation. So here's an example. You can this is the range, so this is the distance. So the antenna is somewhere here, and you are eliminating the image, and then the signal goes back. So this is the range, this is the distance from the antenna, and this is the cross range. This is the one of the transversal, pick any of the 2 transversal directions. And if you look at the image, you see crosses, and this is where the true position of the scatter is. And you see we are not recovering it exactly. For example, in this case, the position of the scatter is recovered in a nearby point. This scatter over here is recovered exactly, and so on and so forth. And then there is a little bit of noise, as you see on the figure that has here. So that's an image window view. I can also look at a solution vector, namely rho is a vector, the vector of reflectivities, and I can look at the values of say, for example, absolute value of the vector of reflectivities, and see the fidelity of my reconstruction. So the previous image, the solution vector for the previous image that I showed you over here, has the following properties. So you see grass sitting over here. So those are the little blue dots that you saw on the previous slide. And then here are the scatterers that you have, and some of them, and it looks like they're this is let's see, it says the green is the true scatter, the position of the true scatter, the amplitude of the true scatter, and red is sort of what we can recover numerically. And in order to find the position, you kind of need to see that they are sitting on the same vertical line. Then the support is recovered exactly. But to see the support better, a picture like that is more instructive. So I will be showing either this or both to demonstrate the possible reconstruction strategies of L1 methods. So this is an ideal situation. That's what you can recover. So you have scatterers and their positions are recovered exactly. And if you look at the amplitudes of the reflectivities, they're also recovered exactly. So red dots are sitting on the green dots. So that's a perfect recovery of the signals. And it is done by L1 methods, and the reason we were interested in sort of incorporating L1 methods our work is because if you use, for example, classical Kirchhoff migration L2, which is an example of L2 methods, what happens is that instead of recovering points or at a single point scatters at a single pixel, resolution starts to kick in, and depending on how far away and how big is your array, you start getting dots instead of points, and then on top of that there is also a lot of noise outside of the true scatters. And as I said, L1 methods became popularized not only in imaging, but also, for example, in statistics, where it was popularized in the words of Donoghue and co-authors, and it was called the basis pursuit, which was the idea that I can recover a good solution, point scatters, sparse solutions of this system, provided I minimize L1 norm of this solution. And it was later proven that for certain classes of matrices, this method gives you exact recovery. Namely, you find the solutions, and either you can use decoherence or incoherence of columns, which basically says that all the dot products of columns are small enough, let's say, or restricted isometry property, which is a slight generalization of this incoherence condition, but for sort of systems of bases of vectors, not two vectors, but many vectors at the same time. So, and the name of the method was given to be basis pursuit, because what you are actually looking, you're trying to find the support of your method. So so you're kind of choosing the basis to approximate this vector. So in this case, you want to choose this column and this column to get this picture. So you're searching which columns of your matrix A, the imaging matrix, are a good basis to represent this the measurements that you obtain. One of the issues with basis pursuit, at least in the imaging matrices that we encountered, was that basis pursuit imaging is unstable to noise. So if you add 40% of noise to this image, then you almost immediately start losing resolution. So this is the situation where this is the true image, and here you see a lot of grass, and some of it's even stronger than the signal. That allows. So one of the things that motivated our construction that I will present soon was the idea that you want to improve stability of basis pursuit. And the idea is this. So suppose this is my original problem, which was, say, unstable if you add noise, but let's improve the condition number of this matrix A, of this imaging matrix A. Let's just add to it an arbitrary matrix C, which we'll call the noise collector matrix, so that the combined matrix A with C has a better condition number and has better stability. So, and then look for solution. Instead of solving this system, let's solve this system. So add an additional fictitious vector raw noise collector as an unknown, and use it with this matrix C, and look for minimizer, L1 minimizer of the pair. Raw image window is a set of reflectivities in the true image window, and raw noise collector is a set of fictitious reflectivities that have no physical meaning whatsoever, but they play a role of regularization or only. And again, if the combined matrix satisfies nice incoherence properties or RIP conditions, then you should be able to find, using this approach, solutions of the noiseless problem exactly, and they will be the exact set of reflectivities that you're looking for. And that's where we started in this construction. And it worked out, and it gave some other applications. So I will explain this this construction and how it actually does absorb noise in the simplest possible case. We started with the linear algebra case, but it also generalizes to natural imaging applications. Namely, one of them is in imaging. Very often the matrix A has coherent columns, especially if you drop down resolution and you have the increased resolution of your images, and you try to in order to get a sharper image. I will mention a little bit some preliminary results, what happens in homogeneous media, but more importantly, there is an observation made by many people that if you're imaging in homogeneous media, it's more natural to image with cross correlations. For example, well, you know, Knut, for example, worked on coherent interferometry, and the question is how we can use this idea of noise collector to image with cross-correlated measurements. So I'll mention that here in this talk. And then there are some other recent developments that don't fit in the format, so I may mention some of them very briefly in the end. So the key, so there are three parts. Say plain vanilla noise collector construction, a little bit of coherence, how you handle coherence, and then the quadratic measurements in the end of the talk. So I had a long introduction. Let me do it a little bit faster now. So noise collector. I will assume for simplicity that the columns of the matrix A all have length 1. You can always normalize it to length 1. Then we constructed the noise collector simply by taking columns C at random. C are columns of the noise collector from also of length 1. So that's what it means, that they live on a unit sphere, and you just pick them uniformly. That's our construction. This is so you can think about all these vectors of the noise collector to be sitting on a sphere, and there are many of them. So how many do we need? We are taking the number of, so sigma is the number of vectors in the noise collector. And we take them to be larger, slightly larger than the number of measurements that you obtain, that you need, and capital is the number of measurements. And that's it. That's the construction. And then the procedure is as follows. You solve, as I said, this basis. You solve basis pursuit with this combined raw image window, which is the true reflectivities, and a raw noise collector, which is fictitious reflectivities. Solve this basis pursuit problem, and what happens if there is no noise? Then there is exact recovery. If the noise is small, then what happens is that you recover the reflectivities approximately, and the noise collector actually absorbs all the noise inside itself, and so sort of you have this decomposition. So in a sense, and this idea that you can use a matrix C to absorb noise was appeared in earlier works. For example, there's one citation I have here by Alaska, Davenport, and Baranyuk for special types of noises. So if noise is, for example, sparse, has a sparse representation in certain bases, then choose this basis over here in the columns of C, and then you will obtain results like that. And the difference in our case is that our noise is general. What we are dealing over here, this E is just general white noise, uniformly distributed on the sphere. And one more sort of natural questions here to be asked is, why don't we use L2, L1 regularization? And one can do that. There is a well, again, developed theory, all in fact coming from, again, imaging. John Clairvaux and Francis Muir in '73 wrote a paper where they introduced what now became to be known as lasso method for or BP denoising in geophysics, in Earth exploration. And then there was a paper by Fadil Santosa and Bill Symes that popularized it. So this is SIAM, one of the SIAM journals, where they also brought it to the applied math community. The method that this L2, L1 method is this. You're just minimizing L2 norm of misfit between your data and your guess and the solution, and L1 norm of the solution of the reflectivity. And then there is a tuning parameter lambda that, depending on your estimate of the strength of the noise, you can choose so that you optimally recover signal. Oops. Yeah. So here is an illustration how the presence of the noise collector improves the image. So this is what this image we already had. There is a noise of 40%. And as I told you earlier, there is instability, and you see a lot of grass. Now, if you add the noise collector, almost immediately all the grass disappears. And if you look closer, you see that you recover all the scatterers exactly. And then there is a little bit of grass remaining, but not that much. So that's an immediate consequence. And here's what you see in the when you look at the vector of rho. This is you just saw the image window view, and now this is the vector view. And if you don't have a noise collector, there's a lot of noise in the image window everywhere. Now the image window is just this piece over here. So the level of noise drops dramatically, and you start seeing the signal. Over here, you still recover some signal, but some signal is completely lost in the noise. And the noise collector plays its role. So all these things over here are fictitious coefficients of reflectivities that do absorb all this noise into the, into themselves, and that's what happens. Now, what you can do on top of that, you can completely remove noise from the image window by introducing weights. The idea is the same. So put a weight in front of, for example, the first reflectivities, and in such a way that it is the idea is that you want to make this weight large enough so it's expensive to approximate noise with the columns of A, but it's not too large so that it's still expensive to approximate signal with the columns of A. And this choice of tau, in contrast to, for example, lasso, could be made the same for all levels of noise. So you don't have to approximate, you don't have to make measurements to estimate the level of noise or make predictions. And such methods, such tuning parameters, such parameters sometimes are called pivotal. So at least in this paper by Beloni, Chernozhukov, and Wang, where they introduced square root lasso method, they call their parameter pivotal precisely because it has the same property, that it works for all noise, for all levels of noise as we do. So, and this is now a full procedure how we can improve imaging properties of L1 method. So if you start with an L1 method and do nothing, this is the picture that you obtain, and you see a lot of noise in the image. Now, if you add the noise collector but keep the weight to be 1, so you don't differentiate between image window and the noise collector, then you do decrease the level of noise. As you see, there is much less grass, and you recover the image, but still there is some grass in the image window. Now, if you add the noise collector, then all the grass in the image window disappear. This is the picture. This, you see, there's nothing. There's no noise over here. And on top, once you recover the support by using the noise collector, you can do L2 projections on the support, and this is the reconstruction. So altogether, what I described, and this is how you see that in the again in the vector view. So what happens if you if your weight is 1, then the noise is kind of all the coefficients, whether in vectors, whether in the noise collector or in the imaging matrix A, play a role of absorbing some parts of the noise. But if the weight is chosen correctly, then everything disappears. There's no noise over here. Everything went to the noise collector. So that's how it looks. And in the end of the day, this is the difference. So you start, if you start imaging using L1 methods, plain vanilla L1 methods, then this is what you have. And if you use noise collector, this is the picture you obtain. So this is more or less the story for the plain vanilla noise collector. And we have the results that supported this picture. So I named 3 of them. The first one says the following: is that no matter what, we call it no phantom signal, no matter what, we can choose weight, so that no matter what kind of noise you have, you never recover anything. So if there is no signal, you will see no grass. There's no noise, no matter. And this result is independent of the strength of the noise. So noise could be as large as you want. If there is no signal, you will see no phantoms. The second result says that if, in addition, that my matrix A has some sort of incoherence properties, so this is the statement of incoherence, the dot product is small enough, where M is the number of so sparsity, the number of scatters we anticipate to have. So if the dot product is small enough, then we are guaranteed that the support that we recover, this is what we recover, is inside the true support. So if you see something, there must be something. We might be missing some of the scatterers, but we guarantee that the false discovery rate, we never discover any, we never make any false discoveries in this construction, provided, as I said, the scatterers are the columns of A are incoherent. And then exact support recovery, namely the 2 supports agree, the one that we recover and the one that we expect to have, provided the level of noise is not too large. So the L2 norm of the noise is essentially, well, there's formula explicitly, but the point is that, as I show, is that it grows proportional to square root of number of measurements. So it could sustain quite a bit of noise in this construction. And this is an illustration. So what I'm plotting over here, yellow is good, blue is bad, and green is something in between. So yellow is the region where we recover all the scatterers. So over here on the x-axis is the number of scatterers that we have. On the y-axis is the strength of the noise. And if the number of scatterers is small, but the noise is big, we recover them. And if the number of scatterers gets larger and larger, then we can sustain less and less noise. And the prediction that I had on in the previous theorem is this line over here. And these are done for several different sizes of the data given over here. So all these results, as I promised you, are non-asymptotic. So they hold for any value of n, and we can estimate all the constants that are involved in these computations as well. So any questions maybe? So so this is a bit busy slide, but the message of this slide is that the algorithm is trivial. The algorithm is just 4 lines. There's nothing. It's just conjugate multiplication by conjugate matrices and thresholding. The computational complexity of this method is the same as computational complexity of the original L1 method without noise collector, because we use some sort of tricks from linear algebra and fast Fourier transform that are written over here. So this is basically Gilbert's trick how to compute fast Fourier transform of circulant matrices. So basically the message that is presented over here is just that there's no additional computational complexity of the of adding the noise collector matrix. And the next topic is specialized, as I said, to imaging. One of the things we wanted to understand is how coherence plays a role in this thing, and there is a natural sort of answer, at least intuitive. You want to so at least let me first illustrate how well what is the natural parameter, how well the noise collector should work. So look, so here's the natural parameter. It's the ratio of sort of what is the best solution to L1 minimization problem. So on top I have this L1 norm of this thing, and at the bottom I have the right hand side. So you try to find all possible, you try to find the worst constant gamma, and that gamma characterizes how well the L1 method will work. So if gamma is large, you can have a lot of grass, as it is presented on this picture. But by adding the noise collector, you can make this gamma to be small, and therefore there is much less grass, as it is depicted on this picture. Coherence. So in imaging, there is a natural way to realize which columns of a matrix A are coherent. They geometrically correspond to points nearby to your scatter. So you can look at vicinities of your points. Geometrically, they just like neighborhoods. Mathematically, they're just columns of the matrix A that are too coherent to a given point. So then if I have an image, for every point, I can define the vicinity of these points, of this point, and then if these vicinities are not overlapping are far apart, then it's intuitively clear we can expect good imaging properties of our algorithm. And here is a result that says that if you can look what happens with the image in the end of the day, you either you have a little bit of grass, and your positions of the scatterers could move a little bit. And these two things you can characterize by incoherent remainder. That's a little bit of grass over here. And the fact that you move your scatter a little bit, so coherent misfit, how much you move your point. And the claim is that both these quantities sort of could be controlled in our case. So the answer, so this is a result that says that depending on the value of this gamma, as I mentioned, the coherent misfit and incoherent, coherent and incoherent part both are controlled by two things: by how big your gamma is and how much noise you have. Delta is the strength of the noise, and gamma is what I had on 2 slides above, or 3 slides actually above, is this quantity that says how big is the value of L1 solution provided the right hand side. And the noise collector makes this quantity to be small. Now, so this is next result. And finally, I will come to the issue with quadratic measurements. So as I said, there was a body of work, I'm mentioning some of it, where it was observed that it's statistically more stable to image with quadratic measurements. And we wanted to explore how to measure with quadratic measurements, again using L1 methods, for the same reason that if you do it with L2 methods, then your method starts to lose resolution. And even in homogeneous media, there are two essentially approaches how you can do that. You either can solve this problem, but that where you actually take absolute values. So here the absolute values are kind of pointwise absolute values. So in particular, in the case where you only, instead of a typical, this is an example where quadratic measurements are just absolute values of your measurements, not cross correlations, but just absolute values of these measurements. But this problem is nonlinear, and its its convergence is very difficult to analyze. Or you can do lifting. Lifting is the idea to bring instead of solving for rho, you solve for the rank 1 matrix rho star. Rho, I remind you, is our vector of reflectivities. And you can do that. You can formulate the imaging with cross correlations in terms of this system as a linear transformation, as I will show you, and there's no issues in analyzing it, but the dimension grows quadratically with respect to rho star and with the measurements, and therefore it requires excessive computational power. So our interest was to be able to use this idea of lifting, but keep the number of unknowns to grow linearly with respect to rho, the number of elements in rho. So the method has 2 steps. One of them is lifting, which is on this picture. And as I said, it was done already previously. And what you do, you treat your vector of unknowns x and think about multiplication, obtaining your data, quadratic measurements, as multiplication by two matrices A and star as a linear map from this space of k squared unknowns to the space of n squared measurements. This are quadratic measurements, where the map is just this tensorialization of the matrix A. But as I said, it has a huge dimension. So instead of solving this map, we look at the k-dimensional vector of squares of the reflectivities and write this whole thing as a linear transformation T applied to only this vector, and everything else is noise. So this is not noise, of course. This is these are coherent interferences of diagonal terms of your matrix, of your row, of your columns of A. But it turns out that they satisfy the same properties, geometric properties, these vectors, if you wish, as noise. And therefore, we can use the noise collector to remove these interferences, even if they are large. So that's the overall picture. We will lift our system to square of the dimension. We formulate it for the diagonal guys only as a linear system and treat the off-diagonal guys as noise, and use the noise collector that I described in the previous half of the talk as a way to remove this noise. So this is the overall strategy as I just described. And again, in this case, it's again the vector E over here. We treat it as noise, as I said, but it's not. Noise. And let me show examples what happens. So imaging. So we're doing exactly that. So we're imaging with cross correlations, and you have you do the noise collector step, and you find the position of the scatters, the support. As you see, the support is recovered exactly for all of them. Once you know the support, you again, as I said, can project or using L2 methods once you know the support, and then you have exact recovery of not only of the positions but also the values of the reflectivities. So this is, I think, noisy data. Yes, noiseless data. So there's no noise, additional noise, but you can also add noise. Picture doesn't change too much again. So this is 10% of noise. So you see first step, second step is the recovery is not exact because you have noise. So L2 approximate gives you the best approximation. And this is 100% of noise. Again, the same thing. You recover the support on the first step, and then by doing L2 projection, you recover the absolute values, but the values of reflectivities. But again, there is an error because of the noise. So this is how it works. But if you look at the image, it looks, visually. Yeah. So, and then one reason, as I said, it's a very geometric reason why the whole thing works, why we can generalize the noise collector to this quadratic measurements idea is the following. the plain vanilla noise collector works for two reasons. For essentially for so for two reasons, and one of them is that if I look at a typical noise vector, so a point on a unit sphere, and ask how, and pick a vector T from any matrix, so fix a matrix T and look at the dot product of columns of this matrix with a typical noise vector, then this quantity is very small. It's 1 over square root of n. You can ignore log over here. It's 1 over square root of length times the strength of the noise. So they're always orthogonal there. And this is a geometric property. And it turns out that if you look at the that this geometric property holds for the off-diagonal elements in the quadratic measurements. And this property becomes sort of this is what essentially becomes when we go from coherent measurements to incoherent measurements, when we image with intensity, for example, only. There we indeed treat the off-diagonal elements as noise, but over here there is still coherence. Nevertheless, it's still these off-diagonal elements satisfy this geometric inequality that allows us. So this, as I say over here, interference vector E satisfies this condition, and then the noise collector kicks in, because this is what the noise collector was designed exactly to absorb vectors that have this property. And then whether they are deterministic or whether they are random, it will work. The noise collector works for that reason, that this is true. And the another advantage of I guess surprising advantage of quadratic measurement construction is that there was the whole construction that I presented was based on coherence of my columns of my matrix A. So I never talked, for example, about the RIP condition, an important observation that if the matrix A has a better property, then in fact we can recover many more scatterers than what I presented in this talk. So in this talk, the number of scatterers I am recovering is of order square root of n, whereas the RIP condition allows you to go linearly with n. But if you do quadratic measurement, it turns out that we also are able to recover the number of scatterers which are linear in n, and this plot is a numerical sort of and it is presented in the theorem, but this plot also demonstrate that this happens numerically. So this little n is exactly this curly n is exactly n squared. So m behaves here. So maybe I should write it here. So m behaves here as square root of curly n, and curly n is exactly as linear n, which is what we have in compressed sensing. So and here is a theorem, as I promised, that says what I showed you on the previous slide, that the number of scatters we are recovering is linear in n, and provided certain conditions on the matrix A hold, which are natural again. Again, it's only about decoherence, and the result is that we have exact support recovery for our method. So Knut, how much time do I have? Is it 50 minutes or what? don't hear you. I'm done. So I don't hear what you said, but I guess you're muted.
You have a couple of more minutes if you want, Alexei.
Okay. I'll just summarize and show one picture. So in summary, I talked about a plain vanilla noise collector, and I did two generalizations. One of them, what happens with coherent columns, and what happens when measurements are made. We do cross-correlated measurements. And again, and it's based on 3 papers. All 3 of them are in collaboration with Miguel Moscoso, George Papanikolaou, and Chrysula Soka. And of course, our main interest is to do the same thing in imaging, in random media, and I will just finish with where random media is basically, we're just changing the speed of propagation using random travel time model. So we just in numerics, we just use for the Green's function, we use the usual homogeneous Green function times a random phase shift for the which is defined as integral over a certain random variable along, which is along the path of coming off. These are the antennas, and then there are scatterers over here. So I just integrate the random variable, the slowness along this trajectory, and that's what this number is, and then I put it here. So if you do numerics for this model, this is what we have. These are several different realizations of the same medium. There are 2 scatterers over here, and the usual sort of the usual things that you anticipate happen. If you do Kirchhoff migration, it's unstable. So the first column is Kirchhoff migration, and you see it's not statistically stable. If you do synthetic interferometry, then it is stable as it is designed to, but it may not separate scatterers, so they may glue together. And if you use noise collector, then you have stable and a well separated image for the scatterers. And I'll stop here and take questions.
Great. Thanks a lot, Alexei, for great talk. So the floor is open for questions now. So please unmute yourself and ask questions if you do have questions.
Hi, Alex. I have a question.
Okay.
Yeah.
Please.
So if I understand correctly, it's basically you do this is because your noise has a sparser representation in the dictionary C, and your signal.
No. This is exactly the point that I'm making. It's not. This method, I have it explicitly on this method our noise has no sparse representation, in contrast to one of these references that I put on the slide, but there are many more. So so let me emphasize that again. So there was work where you could look for dictionaries for noise. So for example, here is one. At least that's where we learned it. But in that work, or in many others, sparse representation for noise. For us, noise has no sparse representation. It's a true Gaussian noise, and in that situation, it has no sparse representation.
So what about if the A is also the columns of A corresponding to the random vectors on the sphere? And how do you split which should go A, which should go to C?
So what this thing makes, there's an answer to that as well. If I don't put weight on my columns of the matrix A, then the noise collector is everything, so to speak. I had an image, but I cannot find it now. Where is it? So I am wasting my time jumping back and forth. Yeah, here, for example, here's an example. This part of the image is noisy. So the noise collector is everything. Because I don't use weights. When I use weights, so it's like here as well. I don't use weights here, and image also plays a role of noise collector. But when I use weights, I absorb the extra noise. So the system, this is done by choosing the tau, the weight. That's how the system knows whether something should go to the columns of A or something should go to columns of C. And the choice of this weight is independent of the noise. There's this no phantom theorem that says you can choose this weight so that you just fix it once and for all, and the system will know which thing should go to the noise part and which thing should go to the signal part. And that's simply sort of estimate on, yeah.
But for example, again, if A is similar to C, so I still do not see if my A is some random measurement, it's also projection on some random vectors on the sphere. So I still do not see how a right-hand side vector can know which part is projected to A, which part project to C, because there's no difference from A and C in terms of statistics or patterns, whatever you say.
This is if something comes, if you take, okay, there is the statement, this geometric statement that I made, that a noise vector is always orthogonal to the columns of A, almost 1 over square root of n. This is a probabilistic statement. It's not true, of course. There is always the worst case scenario where your noise could be aligned with your column of A, and then you are unlucky. But you can estimate this probability, and this probability is exponentially small. So therefore, you never see that. So the system, this theorem is a generic, a general state situation, and you can develop this general state situation that says that in general state, your noise will be always orthogonal to the columns of A, and therefore columns of A will never try to approximate noise. They will never be used to approximate noise. So that's a proper probabilistic statement, and that's another, if you wish, selection criterion why you can do what we construct here. No?
So there's something that is to say that the signal space.
There is an option. You can define signal space precisely. You can define sort of signal space with high probability, even though they are never orthogonal, but a typical vector will be. Basically this geometric theorem just says that signal space is orthogonal to the noise space, and therefore if you get a vector, you just do the orthogonal decomposition, put one in one, one in the other.
That's also not only orthogonal, but it also has sparse representation, right? Otherwise,
yes, it has to. Yeah, of course. Of course. Yes.
Okay, thank you.
Hello, Juan Kai. Hello, Alexei. Can I say something? Because Do you hear me?
Yes,
Alexei?
yes. Hi, Miguel. How are you?
Oh, hi, Miguel.
Good. I'm very happy because I'm going to be vaccinated in 3 days, so I'm very happy. Anyway, can you show you have a slide with the minimization problem where the tau is there is somewhere I don't know what is the not there.
This one?
Not that one. Ah, yes, that one. Yes, that one. No, that one. The one in. So the answer, I think, the easy answer, the intuitive answer is that you have a tau on chi there. A tau is a parameter that is larger than 1. And in fact, is in all our experiments is 2, is the number 2. And that number 2 makes more expensive for the matrix A to approximate the noise, even if the matrix A is the same as the matrix C. So even if A is random, it's still more expensive when you solve this problem because tau is greater than 1.
But this may not be desired, right? Then you just put signal into the noise space.
You lose a little bit of signal.
Yes.
If you see at this picture, all the, on the first step before you do L2 projection, all the amplitudes of the signal are smaller than the true signal. So that's a consequence of noise. In fact, the more noise you have in the system, these guys go down, 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 down. I think I have a picture of that before that, like over here. See, the signal is here, but the one that we recover is down. And why it went down? Because of the presence of noise, because some of the signal went there as well. This noise collector absorbed all the noise, we guarantee that, but it also shaved a little bit of the signal.
Yeah, but this is the magnitude you can shave, but there's also possibility the support is lost, as your theorem said, that basically.
Yes, because you cut and cut and cut, and maybe you start to cut too high. Mm-hmm. You're losing support first. You're losing first the weakest signal, simply because you lose the support because your signal is too strong. Your noise is too strong. The stronger the noise, the lower your recovered signal. That's how we see it, and then you eventually start losing it completely if the noise is too strong.
Yeah, I see. So the really thing is what's the most, your noise should have certain angle or certain perpendicularity to the signal space. Otherwise, it can absorb the signal into the noise.
Exactly. So that's this property that I mentioned, the geometric property that is true not only for noise, but it actually is true for coherent that arises in cross correlation. So this condition over here.
Yeah.
Is what it is. Forget about all this notation. It's just statement that it's proportional to 1/√n. This is 0 basically, right? If n is very large. So all these vectors from the column space are orthogonal to the noise with high probability. And then when we look at our interference vector, it also satisfies this property. This is just a geometric property, and therefore it could be treated as noise. So that's all it is essentially there, to be able to verify this condition.
And also, if your C is too large, you choose too many columns of random noises, and anything goes into there with very sparse. There's a lot of sparsity. Then you can absorb a lot of signal to there, right? If your C is too large.
Again, if you pick it random, it is true, but you can pick it, for example, so that this condition is satisfied. The following condition is satisfied if AJ and CJ are orthogonal to each other, then no matter how many C's I take,
Sure.
it's still gonna behave as I want. Yeah.
But since you take randomly the C in the unit sphere, so right, when you take too many columns of the C, then they can really represent.
You're right. Yes, you're right.
Yeah.
But it has to be really too many, exponentially many, and we never go in that. Yeah.
Okay. Yeah, that answers my question. Thank you.
So any other questions for Alexei? So I was wondering, Alexei, you mentioned in the quadratic measurements case that you you use less than n squared measurements. You sort of randomly throw away some measurements, or how do you do it when you square it?
So we use, so there is a data that I skipped because I didn't have time. For example, on this picture, the dimension of the image, wait, where is it? So what we use is this. We take 21 times the dimension. So it's a linear data essentially. So the total number of measurements is n squared, but we really take 21 n measurements in all the experiments I showed you on this picture. So we don't use all the quadratic measurements. And you know, this is not a problem because the dimension of this vector is also growing linearly with n. So we're really just picking at random, not at random, but you know, picking some linear subset of our measurements to be able to image. Yeah, I mean that's an answer. I mean, we don't particularly. I mean, the most yeah, the most difficult case is to take the diagonal, to take the absolute values, because then there's no really cross correlation. There's no information about cross correlation. So we pick many, or if you pick many off diagonal elements of your matrix B star, then you image very well.
Great. So yeah, still let's a little bit of time if you have a final question for Alexei.
Sounds good.
Well, I think it seems that there are no more questions, Alexei. So thank you for a great talk. This is a very interesting and important problem, and it was
Thank you, guys.
very nice.
Good to see you all.
Yeah, thank you, Alex.